Alright, chemical reactions of carboxylic acids. So the first thing is to show how to make a carboxylic acid. You can only do that with a primary alcohol because it has to be on the end. I'm going to say that we have an oxidation. And 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then it becomes an aldehyde. So we have our primary alcohol becomes an aldehyde after the first oxidation. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then that aldehyde oxidizes and becomes 1, 2, 3, 4, 5, 6 a carboxylic acid. So in this case we add, we take away a hydrogen. That is one of the things we can do for an oxidation. An oxidation is either the loss of hydrogens or the gain of oxygens. In the second step we go from an aldehyde to a carboxylic acid by adding an oxygen to that between the hydrogen and the carbon. So any alcohol that you were given with successive oxidations like that, you should be able to come up with the carboxylic acid. Now, working with benzene rings, with these aromatic compounds, they're very stable, so they're hard to get them to react with anything directly. What you need to do is create a weak point, a substituent on the benzene. So this one already has an alkyl group, but that's not often too useful. Instead, what we like to do is chop this away and put on something more reactive, like a carboxylic acid group. If you have a benzene, you have an alkyl group. This set of reagents is going to trim away everything but one carbon. So if we do that, just going to draw it like that, we end up with that carbon turning into a carboxyl group, and then the other two carbons become CO2. They really get oxidized, and then the remaining hydrogens become waters. So just got to make sure that they're balanced out. If I had another carbon here, we'd have another CO2. We'd have to be careful about how many waters we had there. So I'm not going to go too far here, but this chain, this alkyl group, can keep extending out, and we'll still be left with just one carbon that gets turned into a carboxyl group at the end. Here, when we have an acid that goes into water, this acid gives up its H+, and we produce this and H3O+. So it doesn't matter what else is attached here. If we have this carboxyl group, it's going to give up an H+ in water to produce H3, the hydronium ion, and the counter ion, the conjugate base of the acid. If we want to do it instead of just water, have a base that we're dealing with, we just what will happen here is the H+ will still go with the with this group. Instead of water, it's OH-, and what will happen is the Na+ will be left over. So we'll get the compound. It's been ionized. So that's minus. They have Na+ as its counter ion, and then this H+ and the OH- produce water. So an acid and a base producing a salt and water. That's what they do. Now here, I didn't notice this line. Don't ignore that line. There's no bond between the oxygen and the sodium. It should just be O- and Na+, to show that they're just ions. So there's no bond there. Sorry about that. The editor did that. And but if you have a salt, like we have up here, and we want to get back to the original acid, well, you take that salt and you just add a very strong acid that will push an H+ back onto that O-, and then we'll also have sodium chloride left over. So we have the salt and an acid, and it just reacidifies that conjugate base that has the O8 O minus, and we're back to the where we start. In our labs, we'll be doing that very thing. We'll be changing a carboxylic acid into a salt, and then back to an acid. Okay.